Hello, science folks. I'm hoping that you first got a chance to see the misconceptions on temperature through Veritasium. Great video that does a great job of explaining this concept, but let's review just a little bit to kind of go over that again. We first of all talk about the brass. The brass is a metal. It feels cold to touch. The styrofoam, it feels warm. Now, both these substances are truly the same temperature. They've been in my house all day long, but they feel different. The brass feels cold because it's stealing my heat quickly. Styrofoam actually feels kind of warm because as the heat leaves my hand, it hits the styrofoam. Some of it's absorbed, but most of it's bounced back into my hand. So I get the sensation of warmth, but they're both the same temperature. So a very interesting concept about why we feel things as hot or cold. You've noticed this before. You're at a Caledonia football game and you go to the bleachers and you're excited and you're cheering on, and then you go to take a seat. And when you do that, you get this picture that I drew this afternoon of someone sitting down, and no, they're not going to the bathroom. I understand that's how the picture may look, but they're actually losing heat. Your behind is losing heat and it's going into the aluminum bleachers. And as it does this, you are exothermic. You're losing your heat. Exothermic means losing heat. And anytime you're losing heat, somebody else is gaining heat. And the bleachers, they're gaining the heat. They are endothermic. In this situation, we can apply fake numbers. Let's just say we're going to use the number 300. 300 joules of heat energy are leaving you. Now, if money leaves your bank, that's a negative thing. And that's the case here. Energy is leaving you. It's a negative 300 joules. Now, the bank account for the bleachers, their bank account's going up. They've got a positive 300 joules. That's the energy that they are gaining. So just remember, whenever there's a heat loss, somewhere else there's a heat gain. Now, unfortunately, I just threw this number of joules out, and you're saying, what in the world are joules? Joules are a unit that we use to measure energy. We also use calories to measure energy. You've seen that on your food. They're both used to measure heat energy. It's just like talking about miles and kilometers. They're both units that have different numbers to them, but they're both used to measure distance, and you can convert from one to the other, just like we can convert from joules to calories. Same thing takes place when you're at the bleachers in the gymnasium. You sit down and they steal your heat, but now they're plastic bleachers, so they don't steal your heat as rapidly, so you don't send out a shriek when you sit on the bleachers. So we get into this concept of temperature now, and we say, oh, well, what's this temperature? It measures the average kinetic energy. So the heat's the transfer of energy. If we just measure, well, let's look at all the molecules. How fast are they moving? That's telling us our temperature. And that's what kinetic means. Kinetic energy is the energy of motion. This is your old school picture of the thermometer. As the molecules in that thermometer move faster, they hit each other more often. They space out and take up more space and fill up the column. As the ice pack is applied, it cools down. The molecules don't hit each other as much. They don't need as much space, and they condense, and the thermometer level goes down. We see here in this picture, we can see with the cold, these are supposed to be moving not as fast. These are supposed to be moving really fast. So since they're not moving fast, the temperature's down lower. It doesn't need as much space. These guys smashing into each other and have more friction. They need to take up more space, and the fluid in the thermometer rises. Now, the question becomes, if we continue to make it colder and colder and colder and colder, eventually these will stop moving altogether. And if that happens, what will actually take place is we reach a point where there's no kinetic energy. And if there's no kinetic energy going on at all, that's absolute zero. The average kinetic energy is zero. That's at negative 273 Celsius, or we actually call it 0 Kelvin. We wanted to have a temperature scale where zero really meant zero, because when you talk about Celsius or Fahrenheit, those numbers just don't do it. So the reason we have Kelvin is so that zero actually means zero. There's no kinetic energy at that point. And here we go. I heard this joke about absolute zero. It was okay. Get it? It's like a science dad joke. It's wonderful. So really all of this is what we call thermodynamics. It's all about heat flow. Heat's always flowing from hot to cold. And it will continue to do that. It's a law of the universe. We actually call it the heat death of the universe. Eventually, heat will spread out over the whole entire universe in many billions of years. Don't worry. Until everything is the same average kinetic energy. So we get to this new topic we call specific heat that I can't leave today without you hearing. And that's a concept that says, how much heat does it take to make 1 gram of a substance go up by 1 degree Celsius? So if I take a look at brass, here's that brass again. It would take 0.38 joules of this of energy, sorry, to apply into here to make a gram of this go up a degree Celsius. So that's its number. It's kind of like a fingerprint for it. If we take a look at water, here's some water. Its number is 4.184 joules per gram degree Celsius. That's a tricky unit to say. This is considered a very, very large number. It means it would take 4.184 joules of energy to make 1 gram of this go up 1 degree Celsius. This is actually 11 times more energy than this one. So yeah, it's pretty easy to heat up some brass, and it's pretty hard to heat up some water. You've probably all noticed this at home when you're making macaroni and cheese, and your little brother or sister saying, "Why isn't it done?" And you just shout out, "Hey, you haven't taken science class yet. You don't realize specific heat of water is 4.184 joules per gram degree Celsius. It's going to take a lot of time to get enough joules to make the grams of water go up the correct amount of degrees Celsius to get to boiling." If you don't talk that way to your younger siblings, maybe you can do that with still being polite, but let them know about specific heat. 4.184 joules per gram degree Celsius, a very large number for water. So in closing, please do not forget today, when you touch your silverware, when you touch a glass that you're drinking out of, when you touch a book or something made out of wood, you will sense that it is hot or cold, but it's really what's taking place with heat. Is the heat leaving you and that it's being exothermic, or is the heat going into you? That's endothermic. Everything is always ex or endo. Someone's losing and someone's gaining. Till next time, have a great day.